Work, power, and energy. Sounds familiar, right? Stuff you probably crammed for in a high school physics test. But what if I told you that some of the most basic formulas you memorized, well, they're not the whole story. Today, we're going to dig into the physics you didn't get taught in the classroom. All right, let's just jump right in. If I stopped you on the street and asked for the formula for work, what would you say? Probably force times displacement, right? Almost everyone says that. But here's the thing, that's not quite right. See, the full picture, and honestly it's way more beautiful, is that work is the product of the force, the displacement, and the cosine of the angle between them. Yeah, that little cos theta part, it changes everything. And this actually makes total sense if you just think about it for a second. Picture yourself pulling a rolling suitcase through the airport. You're yanking that handle up and forward, at an angle, right? But the bag itself is just rolling straight ahead. Your force and the bag's motion, they're not perfectly lined up. So what does that cos theta actually do? Well, you can kind of think of it like this. It's capturing the shadow of your force that perfectly lines up with the direction of movement. That's the only part that counts. Only the bit of your force that's actually helping the object move forward is doing any work. The rest is, well, it's just wasted effort, physically speaking.
Okay, so now that we get that, it unlocks this totally wild principle in physics. It's called path independence, and honestly, it feels like it should be impossible.
Okay, imagine this. You've got to get a heavy box onto your roof. You've got two options. Path A, a long, winding, gentle ramp. Path B, a short, super steep ladder that goes straight up. The ramp is a way longer distance, obviously, so which one takes more work? Go on, take a guess. And the answer is, they're exactly the same. I know, right? It sounds crazy. But the work done against gravity is identical. Why? Because while the ramp has a longer distance, the force you need to push is way less. And with the ladder, the distance is short, but the force is huge. Those two things perfectly cancel each other out. In the end, all that matters is the final height you reached. The path you took to get there, totally irrelevant. It just boils down to mgh. So, doing work on something changes its energy. And that energy in our day-to-day world really shows up in two main forms. Let's call them the two sides of motion. On one hand, you've got potential energy. Think of this as stored energy or energy of position. Like a bowling ball held over your foot has a lot of potential energy. Then you have kinetic energy. This is the energy of pure motion. An object has it just because it's moving. Simple as that.
Okay, now this is where things get really interesting, especially when we talk about momentum. Let's compare a tiny speeding bullet to a big, slow-moving bowling ball. If they have the same momentum, which one has more kinetic energy? Well, it's the lighter object, the bullet, because to have the same momentum, it has to be moving insanely fast. Now flip it. If they have the same kinetic energy, which one has more momentum? This time, it's the heavier object, the bowling ball, that wins.
So if you're ever in an exam or just trying to win a physics argument, here's a great little shortcut from the video that inspired this explainer. If the kinetic energy is the same, just remember, the heavier one has more momentum. It's a lifesaver. All right, let's put all this together with an amazing real-world problem. This one reveals a hidden and kind of unfair truth about what equal work actually means. So here's the scene. You and your little brother have a chore. Empty a big, full water tank. You decide to split it 50-50. Sounds fair, right? You each empty half the water. But is the amount of work you each do really the same? So, being the smart older sibling, you decide to go first. You take the top half of the tank, the easy part, leaving the dregs at the bottom for your brother. Now let's think about the work you do. To figure that out, we need to find the average height you lifted the water. Since you're just skimming off the top, the center of gravity of your water is already pretty high up. You're barely lifting it over the edge, so your average lift distance is really small. But your poor brother? Oh, it's a whole different ballgame for him. The center of gravity for his water is way down at the bottom of the tank. So to get it out, he has to lift that water all the way up, through the part you already emptied, and then get it over the top. His average lift distance is way, way bigger. Just how much bigger? Well, when you do the math, the result is actually unbelievable. Yeah, it's 3 times. Your brother does 3 times more work than you did. You both moved the same amount of water, but that supposedly fair deal was a complete scam, physically speaking. And I love how this source video puts it. It's a bit of a joke, but it makes a great point. Understanding physics isn't just for school. It's about fairness. You wouldn't want to get to Judgment Day and have to explain why you took half the pay for doing only a quarter of the work, would you? Okay, for our last big idea, let's look at springs. This is a perfect example of how a simple drawing can show us exactly where a complicated-looking formula comes from. So we all kind of know this intuitively. The more you stretch a spring, the harder it pulls back. This is a nice, clean, linear relationship. The formula is F equals kx, and if you graph it, you just get a straight line going up. Now here is the cool part. The total work you do stretching that spring, it's just the area under that line on the graph. And what shape is the area under a straight line that starts at 0? It's a triangle, just a simple triangle. And this is how we get that famous formula. What's the area of a triangle? It's 1/2 times the base times the height. Well, on our graph, the base is how far you stretched it, x, and the height is the final force, which is kx. Put it all together, 1/2 times x times kx, and you get 1/2 kx squared. It's not some random rule to memorize. It's literally just the area of a triangle. How cool is that? So you see, the big takeaway here isn't just a bunch of formulas to memorize. It's realizing that the world around us is filled with these